Hello everyone, and thank you for attending today's webinar, Comprehensive Textural Analysis of Solid Oral Dosage Forms, Density, Porosity, and BET Surface Area. My name is Jeff Kenvin, and I'm the Vice President of Science at Micromeritics and the moderator for this webinar. Before we begin, we wanted to cover a few housekeeping items. At the bottom of your screen are multiple engagement tools you can use. You may expand your slide area or maximize it to full screen by clicking on the arrows in the top right corner. If you have any questions during the webcast, you can submit them through the Q&A. We will try to answer these during the webcast, but if we run out of time, it will be answered later via email. Additional materials are available in the resource list. We encourage you to download any resources or links that you may find useful. Some networks cause slides to advance more slowly than others, so logging off your VPN is recommended. If your slides are behind, pushing F5 on your keyboard will refresh the page. If you experience any problems during the session, you can find answers to some common technical issues located in the Help Engagement tool at the bottom of your screen. An on-demand version of the webcast will be available after today's webcast and will be emailed to you once the session has concluded. I'm pleased to introduce today's speaker, Dr. Navid Etebari. Navid received his bachelor's and master's of science degrees in chemical engineering from the University of Tabriz and Tehran Polytechnic respectively. Navid further pursued a PhD at Auburn University, specializing in the valorization of agricultural waste into biopolymeric products. Navid joined Micromeritics in April of 2024 and is currently an applications scientist. He specializes in density, porosity, and pore size distribution of porous materials. Navid, it is a pleasure for me to introduce you today. We are so glad you could be here today to share your insights on comprehensive textural analysis of solid oral dosage forms, density, porosity, and BET surface area.
Thank you for the introduction, Jeff. Hello everyone and welcome to my webinar. In this webinar, we will take a look at textural properties of pharmaceutical formed materials. The properties that will be discussed today are density, porosity, and surface area using different characterization techniques and instruments that we have here in Micromeritics. Characterization techniques that we will cover in this presentation are gas and solid pycnometry, gas adsorption, and mercury intrusion porosimetry. The materials that we have investigated are acetaminophen caplets and coated ibuprofen tablets, with the goal of evaluating the effect of coating on textural properties. We also investigate these materials in the whole form as they are, and when we break them in half to see how breaking these formed materials impact their surface and bulk properties. The first textural property that we're going to take a look at is the density. There are different types of densities depending on the technique we use and the portion of the sample volume that is being measured. Skeletal density can be measured by a gas pycnometer, where skeletal volume is determined by gas displacement. Skeletal volume is the volume of sample including closed pores, while porosity open to the surface and accessible by gas is not measured by this technique. To clarify the distinction between these pores, let's take a look at this graphic image and the magnified portion of it. So here we can see the closed pores in white and open pores in blue. The measurements and calculations of AccuPyc are based on the ideal or real gas law. Ideal gas law has been used traditionally in the previous models, but with the newest AccuPyc 1350, we are now capable of incorporating real gas law, accounting for compressibility and non-ideality of gases. The way the instrument works is very simple actually. If we look at the AccuPyc schematics, you can see that we have two chambers, sample chamber and reference chamber. The gas flows to the first chamber, depending on which one we choose, either the sample chamber or reference chamber. The pressure is equilibrated and measured and recorded as P1. Then the gas is expanded to the second chamber using the expansion valve, valve number 4, and the equilibrated pressure in both chambers is now measured and recorded as P2. Using the real gas law for both steps and knowing that the chambers are at the same temperature, we can get to this simplified equation. Now we only need the volume of the chambers, which can be determined by volume calibration using empty chambers and the calibration standard. Based on the filling direction, one of these two equations are used to calculate the skeletal volume of the sample. The skeletal density will then be calculated by dividing the measured volume to the user-entered sample mass. Now let's take a look at the results of skeletal density measurements for acetaminophen caplets. As you can see in this table, we determined the density of whole and broken caplets using nitrogen and helium as analysis gases, with both sample first and reference first as filling directions, and using two units of different configurations, a 100 cc unit with a 10 cc insert and cup and a 10 cc unit with a 10 cc cup. Overall, looking at the results, we can see that the densities using helium are higher compared to those of nitrogen for both whole and broken caplets, regardless of the filling direction and unit configurations. Comparing the results for either of these two gases, we see no significant changes in the densities when we change the filling direction or the unit configuration. When we break the caplets in half, the densities are still the same, suggesting that no open pores are introduced in the broken surfaces and there is no change in density as a result. Next, let's see the results of skeletal density measurements for coated ibuprofen tablets under the same conditions. Overall, if we compare these results to the caplets, we can see that, similar to what we saw with caplets, we have higher densities for helium analyses compared to the nitrogen analyses for both whole and broken samples, regardless of the filling direction and unit configuration. Also similar to caplets, in each of these sets of data for either nitrogen or helium, we see no differences in the results with sample or reference fill or when we use inserts versus cup. But the difference here is, unlike caplets, breaking the tablets in half actually introduced some open pores that are accessible by gas, mainly because of the exposure of the uncoated inner layers of the tablets when we break them. As a result, we see slight increase in skeletal density because of the decrease in the skeletal volume. Let's take a look at final table for the skeletal densities for caplets and tablets. Out of different combination of parameters that I used to measure the skeletal density and the values reported in previous slides, I chose the value from helium analyses with reference fill direction in a 10 cc unit, and we will use these values for comparisons and subsequent calculations for the rest of this webinar when needed. Looking at this table, you can see that tablets have lower skeletal density than the caplets, and as mentioned earlier, breaking the tablets increases the skeletal density slightly, but we don't see any significant difference between densities of the whole and broken caplets. Next type of density that we're going to talk about is envelope density, which can be measured using the solid, medium, or powder pycnometer GeoPyc. Similar to the gas pycnometer, the method is based on the volume displacement. The only difference is here the medium is dry flow powder instead of gas. The dry flow powder is a free-flowing dry medium which will not penetrate into the pores but will only surround the sample, so the determined volume will include both open pores and closed pores. The chamber is a rotating glass cylinder which holds the powder bed and conditions it before consolidation by the plunger at each cycle. The instrument has a stepper motor counter which counts the number of steps that the plunger takes to reach to a predetermined specified consolidation force. Conducting the test with dry flow only, will give the required number of steps for the blank run, while testing with dry flow and sample will determine the number of steps taken for the sample analysis. The height difference, or the difference in number of steps for these two sets, will be converted to envelope volume using a conversion factor which is predetermined for each chamber size. Now, having the envelope volume, the instrument calculates envelope density using the user-entered sample mass. If correct skeletal density is provided to the instrument, which can be obtained using a gas pycnometer as shown in the last section, the instrument will be able to calculate the porosity of sample using this formula. For envelope density and porosity, I tested 3 sets of caplets, all from the same bottle, to investigate the material variability within the same batch. Similar to skeletal densities, we'll look at the results for both whole and broken caplets. The skeletal density used for calculating the porosity for all 3 runs for each of these samples are from the single density measurement that was performed by AccuPyc and presented in the last section. For whole caplets, there is no difference between 3 runs, suggesting homogeneous batch, at least in terms of density and porosity. For broken caplets, though, you can see slightly more variability in density and porosity. This variability can be due to the differences in shapes and sizes of broken pieces not being exactly the same for each of these 3 tests. Also, the uneven edges and shape irregularities, as well as increased number of pieces that need to be tested to accomplish a minimum acceptable sample volume in the chamber, and decreased sizes of samples compared to the whole caplets can all add some errors to the envelope volume measurement by GeoPyc. In these cases, if we can find or fabricate a non-porous material or a material of known porosity with the same size and shape as the tested material and perform a volume calibration using the same number of pieces as we used for the sample analysis, new conversion factor will be determined by the instrument, which can be used instead of the default one to recalculate the envelope density of the sample. Of course, finding this type of material is non-trivial, but can significantly improve the accuracy and repeatability of the results for these type of materials that give problem in the repeatability. Performing the same analyses for the ibuprofen tablets, we see significantly higher variability in tablets, even in the whole form. This actually suggests that the tablets show more variability than the caplets. While this can be due to any differences in any of the manufacturing processes, coating is probably the main source of the discrepancy, since that is the only additional process in the production of the tablets. So the problem might be the lack of uniformity and homogeneity of the coating layer, or the poor repeatability of the coating process itself. If you look at the broken tablets, variability increases significantly compared to the whole ones. This can be partly due to the inherent variability of the tablets compared to caplets, and also again because the errors being added up from the shape irregularities and the uneven edges in the broken tablets. Similar to caplets, possible solution would be a volume calibration using a similarly sized and shaped reference material to achieve a more accurate sample representative conversion factor. So let's conclude the density portion of this study. Before making conclusions, it should be noted that the envelope density values that I've presented in this table and will use for comparison from this point on are the values of the runs that reported closer envelope densities for whole and broken samples for both of the studied solid dosage forms, for caplets as well as the tablets. Because ideally, in the absence of material variability and sample-related shape and size problems that can cause errors in GeoPyc measurements, we don't expect to see a different envelope density for whole and broken samples, simply because the exposed pores upon breaking these materials are still not big enough for the dry flow to penetrate, and we expect the same volume displacement as the whole samples for the broken ones. Having similar envelope densities, the skeletal density would determine the porosities now, meaning a higher skeletal density would translate to a higher porosity. As expected, the tablets are less porous than the caplets, with the coating layer limiting the gas accessibility to the pores. For caplets, no change in porosity was observed when breaking the caplets in half, while for tablets, Since we remove part of the coating layer in broken pieces, as we expected, the porosity would be higher compared to the whole tablets. Second characterization technique that we're going to talk about is gas adsorption. Physical adsorption or physisorption refers to the non-selective adhesion of an inert adsorptive gas to a solid surface through weak van der Waals interactions. Amount of gas adsorbed on the solid surface is dependent on the temperature, pressure, and surface properties of the solid material. Nitrogen, krypton, carbon dioxide, and argon are the common gases used for physisorption experiments. The information that we obtain from a physisorption analysis is in the form of an isotherm, which is the amount of gas adsorbed on the solid at any given pressure from very low pressures all the way up to the near saturation pressures of the analysis gas at a constant temperature. Isotherm is the basis for all calculations for measuring the surface area, pore size distribution, and pore volume. Shape of the isotherm can give us general information about the type of the material under study and type of pores that the material has. In this picture, you can see common isotherms and corresponding sample features. Now let's take a closer look at the full isotherm. The first stage is micropore filling at very low pressure and monolayer adsorption. Then once monolayer formed on the pore wall, the multilayer adsorption takes over, followed by pore condensation and filling up to the near saturation pressures, and finally by lowering the pressure, pore emptying and gas detachment from solid surface happens, giving us the desorption curve. For measuring the surface area, we only need the information from the relative pressure of approximately 0.05 to 0.3, where mono and multilayer adsorption occurs, also referred to as BET range, named after the scientists who came up with the multilayer adsorption theory. With the assumptions listed here, they reached to this equation for the absorbed gas volume as a function of pressure. Linearization of this equation will result in this second equation, where if we plot the left-hand side term versus the relative pressure, we can calculate the monolayer capacity V sub m and BET constant C from the slope and intercept of the generated line. Finally, BET surface area is calculated using this simple formula. If we are interested in finding out the pore size distribution and pore volume using BJH method, we need the isotherm data from monolayer formation all the way to the near saturation pressure, where ending point can give us the pore volume. The picture in the bottom depicts the different mechanisms of condensate filling, starting from the walls of the pore to its core, versus condensate emptying, which starts from the core of the pore outward. For pore size distribution, first we need to know the thickness of the absorbed gas on the pore walls at any given relative pressure before the condensation begins, which can be obtained using the thickness equation. In addition to the thickness of the adsorbate layer, we also need to know the radius of condensate emptying from the pore core, which is determined by the Kelvin equation. Adding the thickness to the radius of the bulk liquid meniscus obtained by the Kelvin equation would give us the pore radius at any given relative pressure in the mentioned range. Now let's take a look at the physisorption data for acetaminophen caplets. We used TriStar instrument for this purpose. In this picture, you can see the magnified pictures of the whole and broken caplets in the standard half-an-inch TriStar tubes. Full nitrogen isotherms were collected for whole caplets and broken caplets. We can get information about surface area and pore size distribution using these isotherms. Notice that we have two sets of isotherms for each sample from two analyses at the calibration intervals of 5 and 20 seconds. If we zoom into the high pressure range of the collected isotherms, you can see that by increasing the calibration time, we get narrower hysteresis loop for both samples, which would result in better accuracy, but at the cost of doubling the analysis time. We also conducted the BET range physisorption using krypton, which will of course only give us the surface area, but with better accuracy compared to nitrogen because of the krypton having much lower saturation pressure. The calculated BET surface areas are shown in this table. As you can see, the results of nitrogen analyses are very close to the krypton analysis. However, we still see some differences between surface area of whole and broken caplets with nitrogen analyses. While comparing the more accurate krypton analyses, we can see that the surface area values are virtually the same for whole and broken caplets. Next, let's review the physisorption data for coated tablets. Since whole tablets did not fit in the standard half-an-inch TriStar tubes, I analyzed them using another micrometrics physisorption instrument, Gemini. The Gemini has larger tube options that made this analysis possible. Also, the Gemini instrument has an additional balance tube, which is at the same temperature and gas dosing conditions as the sample site during analysis. This unique design reduces the free space error and makes low surface area measurements possible with shorter equilibration intervals and using nitrogen as the analysis gas, while obtaining similar surface area results in the same accuracy in TriStar usually needs using krypton as the analysis gas, as well as applying longer equilibration intervals. TriStar was used for broken tablets in similar conditions that were shown for the caplets in the previous slide. Full nitrogen isotherm was collected with 5-second equilibration interval for whole tablets and for 5 and 20-second equilibration intervals for broken tablets. Similar to caplets, with longer equilibration time in case of broken tablets in TriStar, you can see that we'll get a narrower hysteresis loop, but again at the cost of increasing the analysis time 2 times. And just like caplets, krypton analysis was performed in the BET range for broken tablets also. The results for BET surface area of tablets are shown in this table. And you can see that broken tablet krypton analysis gives slightly lower values than the whole tablets. Also, they are still very comparable and very close. We will get back to the pore size distribution and pore volume later in this presentation, but first let's see how the textural properties table for caplets and tablets look like with BET surface area added to the already analyzed properties. The surface area of the tablets were almost 3 times of the caplets, although both can be considered low surface area samples. Broken solid dosage forms had similar surface areas when compared to the corresponding whole samples for both caplets and tablets. Another thing to notice is that broken tablets and whole tablets have slightly different surface areas, which can be due to the inherent material variability in tablets that was shown in the envelope density results earlier, or due to the instrument variability, where we use TriStar for broken tablets and Gemini for the whole tablets. Last characterization technique that I want to talk about in this webinar is mercury intrusion porosimetry. This analysis can be done using an AutoPore instrument. The technique is based on the work required to force the non-wetting liquid mercury into the pores of the material under testing. Hence, larger pores are filled at lower pressures, while smaller pores are filled at higher pressures. AutoPore is capable of applying absolute pressures of 0.2 to 60,000 psi. Force equilibrium between the applied pressure and surface tension of mercury for cylindrical pores will result in the Washburn equation, which calculates pore diameter as a function of the applied pressure. Calculating for the pore sizes based on the applied pressure range in AutoPore using this equation for the pressures of 0.2 to 60,000 psi, AutoPore can provide information regarding mesopores and macropores from 3 nanometers to 900 microns. This pore size scale shows that the overlapping pore size range for gas adsorption and MIP covers mesopores with sizes of 3 to 50 nanometers. Now let's take a closer look at AutoPore design and how it operates. A conductive mercury inside the penetrometer and metal cladding on its stem creates a coaxial capacitor. The instrument measures the capacitance and correlates it to the intrusion volume using a predetermined penetrometer constant. The instrument consists of 2 distinct sections, low pressure ports on top and high pressure ports in the bottom. The low pressure analysis has 2 main responsibilities. First, sample prep, which includes applying vacuum to clean the sample and penetrometer, and also filling the penetrometer with mercury to surround the sample. And second, measurement of the bulk density. The high pressure analysis is to ensure sample is fully intruded by mercury, and with the total intrusion volume obtained from high pressure analysis, we can calculate the skeletal density and total pore volume. With bulk density determined from low pressure analysis, now the porosity can be calculated using this formula. Total pore area can also be measured from total intrusion and pore diameters using cylindrical pore geometry assumption. Here is the results for mercury intrusion for caplets and tablets in form of cumulative intrusion versus pore size from large to small pores. Alternatively, pressure can be used as the x-axis instead of the pore size, which would give us the same graph, only with the pressure ranging from low pressures to the high pressures, since as we discussed earlier, these two parameters are inversely correlated through the Washburn equation. But before analyzing the data and comparing the results for caplets and tablets, there are some important modifications that we need to take care of. These modifications involve correcting for interstitial spaces, blank error, and material compressibility. I will briefly discuss each of these modifications in the next slides. First modification is interstitial spaces. Interstitial spaces refers to the spaces between solid pieces of sample in case of formed materials when we use more than one piece of a sample, or powder bed porosity in case of powdered materials. This can be recognized by comparing the very first intrusion activities that appear in the early stages of low pressure analysis, which translates to the largest pore sizes in the cumulative intrusion graph to the approximate particle size of the sample. For example, in case of tablets and caplets, it is obvious that we will not have pores in the order of 800 microns to a millimeter, so this region in the low pressure analysis is showing up because of the interstitial spaces between samples rather than the actual pores, and should be excluded from calculating the textural properties. Now let's see how some of the textural properties would change before and after applying this modification for whole caplets as an example. As you can see, removing the interstitial spaces would result in significant changes in bulk density, porosity, and total pore volume. Total pore volume is actually the total intrusion volume from the cumulative intrusion data, which is the most important parameter that we should look for in the results, since it's the basis of almost all calculations in MIP. So if we look at the changes in this parameter upon applying interstitial spaces modifications, we can see almost around 14% reduction in its value, which will significantly affect the parameters that we calculate based on the total intrusion volume. Next modification in MIP data is accounting for the blank error. Blank error is caused by compression and thermal expansion of any solid and fluid involved in the analysis other than the sample itself. This can be high pressure fluid, mercury, or even penetrometer parts. Unlike interstitial spaces, its effect is not only limited to the lower pressure or higher pore size ranges, and it can affect both low and high pressure or pore size ranges. One way to recognize it is to see if we have any negative intrusion, meaning a decrease in the intrusion volume and ending pressures in the post-analysis report. As you can tell also from its name, to apply blank correction, we need to collect the data performing the same analysis as the sample, but this time without any sample and using an empty penetrometer. Now let's go back to our whole acetaminophen example and evaluate the effect of blank correction on textural properties. If we compare the values in the second row of the table to the third row, it's evident that blank correction affects all parameters, but only very slightly. For example, comparing the total pore volumes before and applying the blank correction and after applying this modification shows a reduction of only about 1%. Last modification is adjusting for material compressibility. Material compressibility refers to changes in pores sizes and structures as a result of high pressure applied to the sample. This phenomenon can be recognized as ascending intrusion curve toward the higher pressure ranges. Distinguishing intrusion from material compressibility is very important in achieving accurate data. This can be easier to do in some cases, like acetaminophen caplets here, where we have a plateau region after the actual intrusion, followed by a second intrusion curve, which is most probably due to material compression. But in some cases, it's not as easy as this one, and it may be harder, such as the tablets here, where we have almost constant intrusion rates throughout the whole pressure range. In this slide, we will look at some strategies that we can use to differentiate the material compression from actual intrusion. First one is comparing the pore size determined by physisorption and MIP in the overlapping mesopore range, which can be very helpful way. We can also consider matching skeletal densities from gas picnometer to the skeletal densities that we get from MIP, or matching surface areas from BET surface areas and those that we get from the MIP surface area calculations. Although it should be noted that due to the cylindrical pore assumption of MIP for calculating the surface area, the values may not quite match with the BET surface areas, and we may see overestimated surface areas for materials with non-cylindrical pore shapes like ink bottle pores in MIP results. As an example, for an ink bottle pore, if this picture represents the actual pore dimensions, this long cylindrical pore of the same opening as the actual pore would be how MIP assumes it to be, and hence gives higher surface areas compared to the BET, which has no assumption for pore geometry and only assumes a uniform surface on the pore wall. Now let's go back to the physisorption data and see how pore size distribution from BJH calculations compares to the MIP results. First, let's start with acetaminophen caplets. Here you can see pore size distribution by MIP after correcting for interstitial spaces and blank errors in log differential plot. You can see that both whole and broken caplets show a monomodal pore size distribution with a peak at around 500 nanometers. Looking at the peak shape, you can see that whole and broken caplets overlay perfectly in low and high pore size ranges, but in mid-range they deviate, with broken caplets showing an earlier intrusion onset and a broader peak compared to the whole caplets. This can be due to the different compositions and surface properties of exposed inner layer of solid dosage form compared to the surface of whole caplet. However, despite these differences, the total intrusion volume is the same for both samples as shown in this table. If we look at the total intrusion volume from the BJH calculations, you can see that BJH total pore volume is close to zero for both samples, and that's why we don't really need to worry about the BJH pore size distribution curve for these samples, since the total pore volume is zero. So no pore volume detected in mesopore range by physisorption analysis, which means that any peaks that we see in MIP in the physisorption range or pore sizes smaller than 50 nanometers is an artifact generated due to the material compression and should be removed when adjusting for material compressibility. Now let's take a final look at the whole caplets example and see how textural properties change after applying the material compressibility modifications. So comparing the values obtained after first two modifications to the values obtained after correcting for material compression, we realize that material compressibility modification affects all parameters except bulk density, which is expected because this property is determined through low pressure analysis, and modifications at high pressures would not have any impact on its value. Looking at the total pore volumes, we see that there is 20% reduction after applying the material compressibility versus only 1% when we applied blank correction and 14% when we applied the interstitial space correction. The surface area after all these modifications is 15 times less than its previous value and much closer to the VT surface area, although it's still a little bit higher, which is due to the cylindrical pore assumption in MIP calculations as discussed earlier. And finally, if we compare the skeletal density after all these modifications in MIP data to the skeletal density that we get from AccuPyc, we can see that the values are in very good agreement and very close values were obtained with these two methods. Now let's take a look at the pore size distribution for ibuprofen tablets, starting with the whole samples. BJH calculations show that unlike caplets, there are some mesopores in the whole tablets, as you can see in the BJH absorption and desorption curves here. Looking at the MIP pore size distribution, first thing that we notice is the multimodal distribution, unlike a monomodal one that we saw in caplets. If we compare these two graphs, you can see two matching peaks in the mesoporous range. The peak at 21 nanometer is exclusively appeared in the BJH adsorption, while the peak at 31 nanometer is observed in the adsorption curve, although there is a shoulder peak in the vicinity area in the desorption curve as well. In general, for samples having non-cylindrical and complex porosity, BJH desorption and MIP intrusion being pore throat limited processes are usually better aligned, while BJH adsorption is generally better matched with the MIP extrusion curves. So further investigation is required to get better information about pore sizes and structures in the overlapping region by collecting the MIP extrusion as well as higher resolution data, which means collecting more data points for physisorption. Nevertheless, the current information from comparison between MIP and physisorption is enough to conclude that MIP peaks in the mesopore range that are not present in the physisorption data are not actual peaks and are an indication of material compression, which should be removed from the MIP data for reliable evaluation of textural properties. Now let's see the results for same comparison for broken tablets. Similar to whole tablets, we see mesopores present in the same range for broken tablets. As you can see in this graph, the MIP pore size distribution is also similar to whole tablets, showing a multimodal behavior. Again, there is a good alignment between MIP and BJH pore sizes in mesopore range. The peak at 19 nanometer in BJH desorption exactly matched with the same pore size in MIP intrusion curve, while the BJH adsorption peak is happening at slightly different location than the MIP intrusion in the same vicinity, which backs up the better alignment of desorption and intrusion for non-cylindrical pores. But just like the whole tablets, these data show that any MIP intrusion peaks in pore sizes of less than 11 nanometers, which is this area in the intrusion curve, are not actual peaks since nothing is detected by physisorption in this range. So it's safe to say that these intrusion-like activities is shown because of the effect of the material compression and should be excluded from the calculations that we need before interpreting the results from textural properties. Now that we figured out how to apply these modifications, let's compare the modified MIP data for all solid dosage forms. Consistent with previous observations from picnometry, we see significantly lower porosity for tablets compared to the caplets due to the additional coating layer. No difference was observed for whole and broken caplets, while in the case of tablets, breaking significantly increased values of all textural properties as we expected due to the removal of the coating layer. Also, it's worth noting that despite this increase in the pore volume, the broken tablets still showed lower intrusion compared to the caplets, emphasizing the inhibitory effect of the remaining portion of the coating layer. Finally, let's wrap up the presentation with comparison of textural properties through different techniques that we covered today and look at some final conclusions and take-home messages from this comprehensive study. First, porosity comparison for picnometry and MIP. As you can see in the presented porosity data, there are some overall trends that are similar for both MIP and picnometry, such as lower porosity of the tablets due to the coating layer, the fact that breaking the caplets has no effect in their porosity, and broken tablets showing higher porosities due to partial removal of the coating layer. But we should also note the method differences when comparing the results. You can see the porosities obtained from gas picnometry are higher for all samples compared to the ones that we got from the MIP. This is due to the differences in gas and mercury access to the pores, where gas has much easier and better access than mercury, especially in small pores where material compression comes into play in high pressure mercury analysis. So higher volume of open pores are measured by gas picnometry, which leads to lower skeletal volume since open pores are not included, and as a result, we see higher skeletal density and porosity values for gas picnometry compared to MIP. Second set of data that we will compare is the surface areas from physisorption, or the BET surface areas, and the surface areas that we got from MIP calculations. Again, there are some overall trends in BET and MIP data that are similar, such as higher surface area for the tablets and same surface area for whole and broken caplets. But the difference here is for all samples, we see higher values with MIP, and as discussed earlier in this presentation, this has to do with cylindrical pore assumption for MIP and the overestimation in cases that we deviate from this assumption. Besides this, also note that we see an increase in the MIP surface area when breaking the tablets, while there is no difference between BET surface areas of whole and broken tablets. This is because the MIP calculation of surface area is based on the total intrusion volume, which is higher for the broken tablets, and hence we see higher surface areas for broken tablets using this method. And as a last comparison, let's review the pore size distribution and pore volumes determined by MIP and physisorption using BJH calculations. First, the BJH data. These calculations can provide information about mesopores only, so the total pore volume reported by this method is total mesopore volume. For caplets, the volumes are close to zero, so we can conclude that there is no mesoporosity in these samples. For tablets, these values show that we have some mesopores in the coated tablets, and comparing to MIP data can provide further information. For MIP analysis, in caplets, the total volume is the same for whole and broken caplets, which is macropores only, since we established through BJH calculations that there is no mesoporosity in acetaminophen caplets. Also, we realized that the pore size distribution for caplets is monomodal. For tablets, on the other hand, we can see a multimodal pore size distribution for both whole and broken tablets in both macropore and mesopore ranges. While the mesopore portion is the same for whole and broken tablets, a higher total pore volume is observed for broken ones, suggesting that more macropores are available for mercury intrusion upon exposure of uncoated inner layers. Finally, as we discussed in the pore size distribution slides, we saw a good agreement between individual peaks in the pore size distribution obtained using BGH and MIP methods, but further investigation is needed for more accurate comparison of individual peaks, which is doable with collecting higher resolution physisorption data as well as extrusion analysis in MIP. Thank you for your attention. We will now proceed to the Q&A session.